Hello, everyone, and welcome to my DS3 Kaggle workshop. This week, we'll be going over A/B testing. So before we get into the details of the presentation, I wanted to share a little bit about myself. My name is Carolyn Duong. I'm a third-year undergrad at UCSD studying cognitive science with a specialization in design interaction and minoring in data science. Some areas of interest for me include product design, product research, and product management. I'm currently the design team lead for a startup known as Savvy, and I'm also a research assistant at the Pvalue lab at UCSD. So today's agenda, first, we're gonna give a brief overview of A/B testing. We're gonna give you a real world example of A/B testing and then go over a practice problem together. So to start off, what is A/B testing? A/B testing is a methodology used in user experience or UX research. It's where you present two variants, one being the control and one being the treatment. And that is kind of why we call it A/B testing, because we got variant A and variant B. A/B testing is also known as split testing because you're splitting the individuals or the traffic so that 50% of the people experience the first variant and around 50% experience the second variant. Within A/B testing, you also utilize another methodology known as hypothesis testing, which is where you test to see if these two variants perform differently through statistics. So the process of A/B testing is kind of long, but it can be summarized in a few bullet points. First, you got to formulate the hypothesis, choose your control group and treatment group, that being who's going to experience variant A, who's going to experience variant B. You have to choose a sample size so that it is representative of the larger population. Then you have data wrangling, you got sampling, then you got visualizing the results, most oftentimes in the form of a histogram. Then you got to test your hypothesis through hypothesis testing and then conclude your results. That being, are your findings or results statistically significant? Now, when you are doing A/B testing, you can run into statistical errors, but we want to avoid this as much as possible. And there are a few ways to do so. Firstly, random sampling. Random sampling is where you randomly distribute visitors or individuals amongst the two variations, meaning when you have a group of people you are working with, you can't pick and choose, which variant they will experience. You just have to let them experience it randomly. That way, it is more representative of the population. Second is confidence interval. Confidence interval is the probability of wrongly rejecting the null when the null is correct. And it's also how confident you are about the results. So you'll have the null and alternative hypothesis. So the confidence level is basically, when you reject the status quo in favor for your alternative view, when the status quo is actually what's happening in the real world. So you want to set a confidence interval before going into hypothesis testing. You also want to do the same for the confidence interval. This is a little bit different. Confidence interval is the range of values where we're fairly certain the true value lies within. And it also includes the margin of error. So because we can't test the whole population, we are sampling, meaning taking, groups of individuals from the larger population. And because we're doing this, we can't actually attain the true value of the population, and we can only give a really good estimate. And that estimate also includes a margin of error to take into consideration the fact that we didn't get the information from every single person within the population. The last thing is sample size. Sample size is the number of participants in the test. And normally when you have a larger sample size, it reduces the margin of error, making your results more accurate, I would say. there are normally ways for you to figure out the minimum sample size to have a credible reading of your results, but I will not be covering that today. But you just want to make sure you have a large enough sample size. All right, so a real world example of A/B testing. So this was the Obama campaign back when he was running for president. He had this webpage where people could sign up or get involved with his whole campaign. And so the people behind this wanted to see if there was a way to increase the sign up rate by just changing the way the landing page looked. So in this example, um, they came up with 24 combinations of web pages just by changing the button and the image in the middle. And so throughout this test, they had over 300,000 visitors come to the website, which means that around 13%, or sorry, 13,000 visitors saw each variation of the web page. And they measured the sign up rate. And what they saw was that the most effective landing page was one with a family image in the middle and a learn more button instead of the sign up button. So this was the one on the left was the original, and the one on the right is what was found to be most effective in having people sign up. And it wasn't just like a little bit of improvement. There was actually a 40.6% improvement in this. So this goes to show that the layout of a website can definitely change the conversion rate or the sign up rate. And it's definitely very crucial to do A/B testing. Next, we'll move on to a practice problem. So this practice problem was actually taken by someone named Sylvain Trung on the Towards Data Science website. And so it revolves around the Sephora website, specifically their landing page arrangement. So on the left side, this is the original arrangement. And then on the right side is the arrangement we want to test to see if it is more effective in bringing more people to make transactions. So we want to figure out if reformatting the landing page will increase the conversion rate, or in this case, will it increase the proportion of visits ending with a transaction on the website? So to start off, we split the traffic 60-40, so 60% of people seeing version A and 40% seeing version B. We're not doing 50-50 here because we are concerned that this new version, version B, will bring about losses. So we want to be safe and have most people see, or a bigger portion of people see version A. And we run these tests for 7 days. Remember, this is just an example. It's not like a real thing that happened. So let's say that this is the outcome. We see that version A, the original version, around 6,000 people came to the website and spent an average of 60 seconds there with a standard deviation of 40 seconds, and around 1.5% converted, or 1.5% ended up making a transaction. Whereas for version B, we had 4,000 people visit with an average of 62 seconds spent on the website and a standard deviation of 45 seconds. And a conversion rate of 2%, meaning 2% of people that visited these websites also made a transaction. Now, looking at just these raw numbers, you're probably asking yourself, because version B seems to have a higher conversion rate and higher average time spent on the web page, does it mean that version B brings improvement? Is it better? Or are these differences in numbers just due to chance because, we took a sample from the population? And also, how confident are we in our results? Now, we can't actually claim any of these. We can't say that version B does bring improvement or it is better than version A, because the results, as I said, are samples of the larger population. So instead, we have to carry out hypothesis testing, which is the next step, to see if the results we found in this test are significant. So first, we have to state the null hypothesis and the alternative hypothesis. The null hypothesis basically is a default position to be tested, or the situation as it is right now, or the status quo, what we believe to be true. And the alternative hypothesis is a challenge to the status quo. It's saying, no, the hypothesis isn't correct. Instead, XYZ is the case. So it's what the researcher believes to be true, and we're trying to test if it indeed is true. So for this practice problem, the null hypothesis would be that the conversion rate across the two versions is the same. And the alternative hypothesis would be that the conversion rate is actually higher for version B, and that the differences we saw in the conversion rate and the numbers that we saw is actually significant. And because conversion rate depends on binary values, that being not converted or converted, you could also use the chi-square test in addition to the z-test. However, in this presentation, we're going to go over the z-test since that's the most common hypothesis test. All right, so there's a lot of math and a lot of code here, but the bottom line is to test to see if the alternative hypothesis or the null hypothesis is in favor, we have to calculate the test statistic, which is some parameter or variable calculated from the sample data that we have. And it's used to determine whether or not to reject or fail to reject null hypothesis. In this case, our test statistic is the z-score, which is the formula up on the left-hand corner. So the top is basically the difference in means of version A and B. And the bottom is the square root of the variance of version B over the number of individuals that experience version B, plus the variance of version A over the number of people that experience version A. The z-score can also be calculated just through code. So this code is using Python, NumPy. And right below the formula for the z-score, we have the formula for variance, at least for binary values. So it utilizes the mean a lot here. And once we have the z-score, we can also calculate the p-value, which gives us the probability of obtaining the sample statistic that is similar or more extreme by chance alone, if the null hypothesis were to be true. So in this code right here, we're using NumPy and SciPy stats. Mu B and mu A is what we use to calculate the numerator of the z-score. Mu B and mu A in this case is the conversion rate that we found. Var B and var A here is the variance for version A and version B. NB and NA is the number of people that experience each version. Then we got the z-score formula here, which is the exact same as this one. And then to calculate the p-value, we use norm.sf and then insert the z-score. So what we see is that our z-score is 1.84 and our p-value is 0.03. And if we were to plot this on a histogram in a Gaussian curve, we see that this shaded region on the right-hand corner is our p-value. And the p-value starts where our z-score is. So this is the probability of obtaining the sample statistic, which is 1.84, something similar to that or more extreme, and more extreme being to the right of it. And the p-value is ultimately the thing that decides whether or not we reject or accept, or sorry, whether we reject the null hypothesis or fail to reject the hypothesis, the null hypothesis. So if the p-value is less than or equal to our significance level, we would reject the null hypothesis in favor of the alternative hypothesis. And likewise, if the p-value is greater than the significance level, we would fail to reject the null hypothesis. There are different significance levels you can actually use. The standard is 0.05, meaning a 95% confidence interval. Although in some cases you might have a significance level of 0.1 or 0.01. It really depends on the situation. Normally, if there's a lot of risk involved, you would choose a lower significance level so that you would have more confidence in your results. But in this case, we'll just use 0.05. Because our significance level is 0.05 and our p-value is 0.032, we would reject the null hypothesis in favor of the alternative hypothesis because the results are said to be statistically significant, right? So our test statistic, our z-score 1.84, is very unlikely to happen if the null hypothesis were to be true. And that is why we're rejecting the null hypothesis. Now, note that, when doing hypothesis testing, we aren't trying to prove the null hypothesis. Therefore, we can't say we accept the null hypothesis. We can only say we fail to reject it because, we can't reject it. We don't have information to say we can accept it. All right, so that was an overview of the practice problem. You can also take a look at it in the original article right here by clicking this link. I also listed some other resources here for you, such as an article that goes over confidence interval, confidence level, sample size, stuff like that. And I, along with another DS3 committee member, did a workshop recently about hypothesis testing during the data hacks. And there is some overlap in its contents. So I would encourage you to take a look at the presentation slides for that. You can click this link here. Last things, a few tips for A/B testing. You want to trust the statistical significance of your experiments and not let your personal opinions or your gut feelings get in the way, because what we're doing here is very technical and mathematical. It's more accurate than what you feel in the inside. Secondly, you want to make sure to balance how many people see each of the different variants. In other words, balance the traffic. Like I said, we don't want to pick and choose who sees what. We also want to make our samples as representative as the larger population. And by balancing that, you're able to do so. Lastly, A/B testing is iterative. It's a process that is continuous. You don't just do it once and then you're done. Just because one test went well doesn't mean that you stop there. Once you've found a version with a higher success rate, that becomes the control version, and then you test it again against another version and see, it just goes on and on. All right, so that's all I have for today. If you have any questions, you can feel free to reach out to me or refer to this slide deck or the slide deck for the hypothesis testing. And I also listed some resources here for you to use. But yeah, I hope this was helpful. Thank you.